All right, guys. So, welcome back to Honors Chemistry. So, today we are going to talk about a few things. We're going to talk about the metric system, otherwise known as the SI system, and we're going to start talking about unit conversions and how we do that. So, pay attention. Hopefully, you're a little bit familiar with the metric system because we are going to use it for the rest of the year this year. So here we go. System International de Units. So the SI system. Scientists need to report data that can be reproduced by other scientists. So we need a common reporting system. That common reporting system is the metric system or the SI system. Now, I need to update this because it says here in 1960 that an international committee of scientists met to update the existing metric system. That actually happened just a couple of years ago. So, like just a couple years ago, the kilogram was redefined and a whole bunch of other things were redefined. So, I'll need to update my notes here. But anyway, of course, they came up with this system in Paris, France in the 1700s. In fact, it was Napoleon's science czar or science ambassador that came up with the original metric system. So they still meet in France to reconvene and do things. So there are 7 base units in the metric system. And these are our basic units that we have. So the base units, time is in seconds, and yes, we still use 60 seconds per minute. Everything else, though, is base 10. So length, the basic unit is a meter. Mass, it says kilo, but I disagree because kilo is one of the prefixes. I would say our base unit here is mass. Most people use kilograms because kilograms are more usable, but in chemistry we use grams because grams is pretty small, and we usually do small things in chemistry. So just to give you an idea of how small a gram is, if I had 1 milliliter, just one little tiny milliliter filled with water, that would give me 1 gram. By the way, that is the definition of a gram. At one point it was. Okay, temperature. It says temperature is done in Kelvin. It's also done in degrees Celsius. And more often than not, we're going to be using degrees Celsius unless we're using standard temperature proceedings, because really Kelvin and degrees Celsius they kind of mesh really well with each other. The amount of a substance, this is probably a unit that you've never heard of, but we're going to do it a lot here this year in chemistry. It's a mole. And a mole happens to be 6.022 times 10 to the 23 items. It doesn't really matter what we are counting. It's just 6.022 times 10 to the 23 items. We could be counting cars, we could be counting donuts, but usually we're counting atoms or molecules. Okay, electric current is done with amperes, and light intensity is done in lumens or candelas. So you are going to be doing amperes and candelas or lumens. This is mostly going to show up in physics. If we do get to do a lot of redox, we might finally get to use amps in chemistry for Coulomb's law, but I'm not sure we're going to get there. Coulomb's or the Faraday constant. Okay, so now we all know that time or any of these meters, mass can be really, really small or really, really big. So we don't want to be held to just measuring things in seconds. Could you imagine measuring days in seconds? That would be horrible. So we've got to have different magnitudes to give us different sizes of things. So to better describe the range of possible measurements, scientists add prefixes to those base units. These prefixes are based on units of 10. So this is all powers of 10. For example, kilo means 1,000. Or we could also write it in scientific notation, 10 to the 3. So an object of 5,000 grams could also be written as 5 kilograms. Okay? Prefix milli means 1/1000th. So in fraction form, 1/1000th or 1 times 10 to the negative 3. So an object with a length of 0.00035 meters could also be written as 0.35 millimeters. Now, let's go to those prefixes. These are the standard prefixes. And I need you to understand and know the value, the magnitude, or how big or how small these are from mega all the way down to nano. Okay, so I need you to know these magnitudes. By magnitudes, I mean how big or how small these are. So giga is 10 to the 9th, or a billion of whatever base unit we're talking about. So gigagram would be a billion grams. Okay, mega is a million. So if I had, whoa, what just happened? Where did my stuff go? So if I had a mega meter, I would have a million meters. Okay, kilo means 1,000. So just like a kilogram is 1,000 grams, or a kilometer is 1,000 meters. And then we have our base unit, which is 10 to the 0. Okay, I want to point out something here. Do you notice that all of these units that are larger than our base unit, these are all Greek. So if we have a Greek prefix, we are getting bigger than our base unit. Okay, and then here we go to our smaller base units. So deci is 1/10, or 10 to the negative 1. Centi, a century is 100 years. So centi is 1/100th of whatever we're talking about. So a centimeter is 1/100th of a meter. Milli, a millennium is 1,000. So milli is 1/1000th, or 10 to the negative 3. Micro is 1/1,000,000th. And look at the symbol for micro. Micro is the Greek letter mu. It's kind of like a U with the tail on the wrong side of it, a lowercase u. So micro is 1/1,000,000th of something, or 10 to the negative 6. And nano is 1/1000,000th of something. So if I have a nanometer, I have 1/1000,000th of a meter. We usually measure light waves, so light wavelengths, in nanometers. The visible spectrum for light is about 400 nanometers to about 700 nanometers. Those are the wavelengths that our eyes can actually see with visible light. And then pico is, so we go from billion to trillion. So pico is 1/1000,000th of whatever we're talking about. So notice also that these smaller prefixes here are Latin. Okay, so our bigger prefixes are Greek, our smaller prefixes are Latin. Okay, so let's do a little bit here. What is the name for 0.1? Or if I look at 0.1, it's a 10th. So if I go to a 10th, that name is deci. So the name for 0.1, or a 10th of a meter, is a decimeter. Okay, we would abbreviate this. Notice all the lower or the smaller prefixes are indicated by lowercase letters. So I would indicate that by a little d and a little m, decimeter. Okay, so if I formed a cubic box with a decimeter on each side, let's see how good my art skills are on a tablet. Not awesome, but I'll take it. So if I have 1 decimeter here and 1 decimeter here and 1 decimeter here. So I have my height. Let's switch my color. I have my height here. I have my width here, and I have my depth here. Okay. So if I have 1 decimeter on each edge, what would the volume of the box be? Remember, volume is length times width times height. So if I did 1 decimeter times 1 decimeter times 1 decimeter, why did that do that? I think I'm getting 1 times 1 times 1 gives me 1, right? 1 cubed, but my unit cubes, correct? So I would have 1 decimeter cubed, okay? So this is a volume that we actually use quite a lot, even here in the United States. The United States, and this is my little soapbox, the United States is pretty much the only country in the world that does not use the metric system. And for the life of me, I cannot figure out why we have not joined the rest of the world in using the metric system. Whenever I travel internationally, for example, to visit my family in Canada or to visit my exchange students that I've hosted from Chile or Italy, I can't figure out why we're not using the metric system. It's so much easier. Okay, so think about this. What would be about a decimeter for those of you who are familiar with, that little ruler that you've been using since probably first grade is 10 centimeters on the side. So think about it. You're going to have about 10 centimeters by 10 centimeters by 10 centimeters. Think about something that would be about that size. Okay? This is a liter. And a lot of things, especially soda pop, are sold in 2-liter bottles. So if I had 2 of those 10 decimeter cube boxes back to back, that would be the size of a 2-liter bottle, like you get soda pop in. Okay? So instead of using decimeters, we're going to use centimeters this time. So if I draw that same box, and I put 10 centimeters on this side, that is a horrible 10. Let's try that again. 10 centimeters here and 10 centimeters here. Let's see, 10 centimeters by 10 centimeters by 10 centimeters. Okay, 10 times 10 is 100. Times 10 again is 100 times 10 is 1,000. So this would give me 1,000 centimeters. And that would be 1,000 centimeters cubed. And we just said that that would be equal to 1 decimeter cubed. And we also said that a decimeter was equal to 1 liter. Okay? So this is the main point of this whole argument, is a decimeter cubed is equal to 1,000 centimeters cubed is equal to a liter. Another thing I want to tell you is 1 centimeter cubed is equal to 1 milliliter. So this is also equal to 1,000 milliliters, okay? Because a centimeter cubed is the same as a milliliter, okay? We are going to use this conversion, especially centimeter cubed equals milliliter and 1 liter equals 1,000 milliliters. A lot. So this is probably some conversion that you're really going to want to know. So get that in your head. That's probably something that's worth memorizing because we're going to use that a lot. Okay? All right. Now, metric conversions you've probably just done them by moving the decimal around. So we usually do them a little bit differently this in chemistry and also in physics. We like to do what's called unit analysis. And when we do unit analysis, you're going to probably think about this as being way too cumbersome or way too much writing. But I promise you, in the end, it will save you. Remember when you first started secondary math 1 or algebra, and you had an equation kind of like this, x plus 3 is equal to 7, and your math teacher's like, okay, solve for x. And you're like, well, duh, that's 4. It's easy. I can do that. 4 plus 3 is equal to 7. I don't even need to say to move that around. But your algebra teacher is like, no, I need you to take this and manipulate it. So I need to go x plus 3 minus 3 is equal to 7 minus 3. So that you got in the habit of writing your steps so that in the end, you could figure it out, right? So this would give you x is equal to 4. Remember when your math teacher made you do that and you were like, oh my gosh, it's going to feel like that when we first do this. So I want to just do one example, and then we're going to start doing some more examples next time, okay? So we are using dimensional analysis as another name for unit analysis. Other people also call it factor label. So my chemistry teacher in high school, and I think I just misspelled that, factor label. Why won't that erase? You'll notice that I really do not spell well because, and I'm going to share a little secret with you, your teacher has mild dyslexia. And you know what? That's okay. We all have our learning challenges. It doesn't mean that it's going to stop you at all. Okay? So don't let your learning disabilities ever stop you. Okay? Little side note from Mrs. Banks. Okay, learning to read was really hard for me. But hey, I made it, right? And I love to read now. So convert 4.75 grams to milligrams. So the first thing I've got to do is I've got to figure out how many grams or milligrams go into the other. So I know that grams are larger. So I'm going to put 1 gram as my base unit. And I usually want to use my base unit to be the 1. That is the 1. So in 1 gram, milli means 1,000th th. So that means I have 1,000 milligrams in 1 gram. So I want my grams to cancel. And when I have a number on top of a number in fractions, they reduce out, don't they, to 1? But if I have a unit on top of another unit, they don't cancel out. They don't factor out. They cancel out. They totally go away. So if I have grams on the top, that in the next step, I want it to be on the bottom so that it will cancel out and go away. So I'm going to put my grams here on the bottom. And because I want my answer to be in milligrams, I want my milligrams to be on the top. Okay, so notice gram unit divided by gram a unit, that's going to totally cancel out. So I can totally get rid of that grams. And then we just have the math to do. So we're going to do this just like ordinary math. So anything that is on the top is going to be a multiplier, and anything that is down below, we are going to use as a divider. Okay, so if we divide by 1, it just gives us the same number. So I can essentially ignore that. So I really just need to focus on 4.75 multiplied by 1,000. So that will give me, I don't have enough room to write that, 4,750 milligrams. Now, with sig figs, now this is the thing that we need to really think about when we are doing these. Now, I've got 3 sig figs here. Now, the way I've written this 0, because I have no decimal point, does not have any significance. So I could write it this way. That would be totally acceptable. That still only gives me 3 sig figs. But I could also write it in scientific notation as well. Okay? Now, the other thing I want you to notice is I only really cared about the sig figs here. Why didn't I care about the sig figs here? The reason I didn't care about the sig figs here is this is a definition. Because it is a definition, anytime I'm converting within the metric system, I am going to have infinite number of sig figs because we're going to use definitions to convert. So when we are only converting within the metric system, the only thing that really matters on counting sig figs is our initial number, because we're going to be using definitions for the rest of it. Okay? Now, the other thing I wanted to point out, notice I also was very careful to add units. Every time we have a measurement, we always have to have units. Why do we need to have units? If I have 4,750, but I don't know what it is, do I have any idea what we're talking about? Units help us understand the context or what type of measurement we have. Okay, it would be way different if I had 4,700 kilograms or 4,700 megagrams than milligrams. So this helps us understand how big or how small and kind of the context of what we're actually measuring. So here with the milligrams, I know that I'm doing mass, and milligrams are relatively small. So I know that this measurement is relatively small as well. Okay? All right, that's enough for today. We will do some more unit conversions and work on unit analysis on our next time. So have a great day, and we'll see you in class. Bye.